Okay, so continuing on, we're going to plug this basically into a calculator right here, and we're going to get 0.6 minus 0.036 plus 0.000648. And if I simplify that, I get 0.564648. So this is my approximation of sine of 2x when x is 0.3, according to Taylor's theorem. So if I want to see how close I am right here, let's plug in the actual value of 0.3, where I have sine of 2 times 0.3. And if I plug in sine of 0.6, that gives me a value of 0.56464247. So as you can see, we're very, very close right here. This is a very good approximation right here. Now, if I want to really see where I actually am versus where I think I am, and see just how far off I could be, and of course the question says to prove that it's less than 1,000th off inherently, let's take a look at the Lagrange error bound. So here, I'm going to say, well, up here I have the third order Taylor polynomial, so the next derivative is going to be the fourth derivative. And I have 2x instead of just x to the 7th power. Why the 7th power? Because I go odd numbers with sign, 1, 3, 5, that means the next term is 7. All this over 7 factorial. Now one thing right off the bat, the fourth derivative is again just sine. Trig functions repeat every fourth derivative, and if I take the fourth derivative of sine, I'm right back to sine. And sine has an inherent maximum value to it. Its maximum possible value is 1. That's true over all intervals in any interval. So immediately I know the maximum possible value of this fourth derivative is 1 right here, and it doesn't matter what interval I look at. If, on the other hand, the problem specified that we were looking at an interval from, say, 0 to 0.3 right there, where we were not just looking at any arbitrary interval, and we had one specified, let's use that as an example real quick, 0 to 0.3. I would have to ask myself, okay, what is the sine function doing between 0 and 0.3? Sine of 0 is, of course, 0. And if I go sine of 0.3, I get a positive number. So sine is increasing over this interval. So technically, if I want to maximize the sine function over that interval, I need to take the largest value and plug that in for my sine function. In that instance, that would be sine of 0.3, which is equal to 0.2955 roughly. So this is how we would get the true maximum value of the derivative over a given interval, and if they don't specify an interval, then we inherently use 1. The same thing would apply for cosine, because they both have an inherent bound of 1 over any interval, and if we have something more specific, we can get smaller than 1, because we know just where to look. So in this case, let's do it both ways, just over an arbitrary interval, where I'm looking at 1. I'm going to say this derivative goes to just 1, and I have 2x to the 7th. 2 to the 7th power, 2 to the 5th power is 32, so 2 to the, let's plug it in to make sure, 2 to the 7th power is going to be 128. And 7 factorial is going to be 5,040. Now, doing a little bit of quick work, if I were to reduce this, I can reduce that all the way down to 8 out of 315, x to the 7th. So if I'm doing this over any interval at all, I'm basically just going to pick my point, any point I wish, plug it in for x, take that to the 7th times 8 to the 315th. On the other hand, if I'm interested in, say, this interval right here, something very specific, all I will do is take 8 over 315 times 0.3 to the 7th. Plug that into my calculator. And I'm going to get 0.00002187 for that. And of course this right here is assuming that I'm just using the 1, but if I'm going to specify an interval, then I can get my sine function even less than that. So instead of multiplying this times 1, I can multiply times this decimal right here. So if I take that times that, I can reduce my error even further and get 0.00005554 roughly. And as we can see, both of these are well within 1/1000th. So I did not have to specify an interval to get my estimate within 1/1000th. I have tenths, hundredths, thousandths. So my first positive decimal here is in the 10,000ths place. So I did not have to specify an interval to get my estimate within that acceptable range. If, on the other hand, there had been, say, a 2 here, then that's what I would have done. I would have had to specify some interval and gotten a smaller sine value in order to get it even lower.